So in this one, we're going to be doing some of the mathematics library stuff, specifically the matrices, like vector 2, vector 3, vector 4, matrix 4x4, matrix 3x3. We're going to clump all of those into the same package so that they can be better optimized and do inlining and all that sort of stuff, rather than separating those out. You can think of this as a pseudo um, linear algebra folder. I like to start with vec3 when I do engines just because that's kind of the most used. Um, and so, yeah, I'm just gonna get started on that. We're gonna be able to um, work with strings, so we can take in strings and serialize strings, all this stuff. So that's why I'm gonna need format, and then I'm gonna need math. So typically, you would do a type vec3 struct, but we are not going to do a struct. We're going to do a type vec3, and we're going to make that a 3, and it would be a float 32 because we're planning on doing regular 32-bit floating point precision for Vulkan and OpenGL, but we want to leave the flexibility for swapping to 64, float 64 later. So I'm just going to add in a config file inside of this matrix package. And what we'll do is we'll say type float is equal to float 32. So that'll just be what we work with here. And so we'll use float there. The reason we use an array is because when we're going to be communicating with the GPU, it's a lot easier just to pump an array in instead of doing all this kind of pointer casting and all this other nonsense. So it's just a lot easier to work with in general. So we're just going to have a couple of extra helper functions that we're going to work with here for getting and the X, Y, and Z, and just a bunch of helper functions I like to add in for Go when I'm writing out these guys. So we're going to have an X, and we are going to return this. Now, instead of using indices here, because we're going to have a bunch of different kinds of vectors, oops, I'm going to use these guys, so just stay there for now. I guess it'll put it in when I need them, but whatever. So instead of using like 0, 1, 2 everywhere, just to make it a little more readable, we're going to use const, and we're going to say Vx is equal to iota, and then Vy, Vz, and Vw. Just to make that more readable when we're using it. It should figure out Z. And now, obviously, we don't have a W. I don't know why it thinks we do. But I also like to get a pointer to that to the vector here. Oops, I don't know why I did that there. I call it px. Yep, py, pz, and then we're gonna have some set functions, just because it's nice and simple. Cool. And then we're gonna have a way to convert this vec3 as a vec2 as vec2, and we are going to return a vec2 there. And because this is going to complain here, I'm going to go ahead and stub in the vec2 vec2.go. Generally, I copy whatever I have. I'm just going to delete these and let it make them when it needs them. Generally, I just copy whatever is inside of one of them, or from the vector3 to all the others, because most of the functions are going to be similar. So I'm just going to copy all this, paste it over here, call this vec2 with the 2, get rid of the x's or the z's here, and I will leave it like this, and we'll come back to it later. Oops, I forgot to change these to vec2 here. Okay. So now we have our as vec2 function, and then we want a function for returning the x, y, and z as just 3 variables. This is just a bunch of helper stuff to start off. And a lot of these will be inlined by, a lot of these will just be inlined because they're so small. And XYZ is helpful because then you can, when you have functions that take in an X and a Y separately, or an X and a Y and a Z separately, you can just say XYZ and get all 3 of those without having to put it into a variable and then take it out of the variable and get the individual components. I just like a lot of helpers. It doesn't hurt anything. So I have a helper for a new vec3, and I have a function for getting this from an array. So we're basically adding in all the functions that constitute creation of this vector3. So we're also going to get from a slice. From slice. I know you can combine those two, the vector3 and the array and the slice ones, but having them separate is what I prefer. And then we're gonna have a function for when we get to Vulkan, we're gonna have to align vector3s as 16 with a we're gonna have to align them by 4, 8, 12, 16 byte alignment. So we're gonna have as aligned 16, and this is just to make it more readable when we see that code, that it's going to return an aligned 16. It's going to pad that with a 0, just so that we have it aligned with the GPU. And then we're going to have a method to. I have a explicit method to converting it to a float64, which may be useless here and probably somewhere else, so I'll skip that one. I'm working off of some of my old code that I've done before, and we're just going to be improving things as we go along. So we're going to have an add other vec3. So this will add these 2 vectors together and return a vec3. I'm sure it can figure out most of this stuff, so I don't have to actually type it all out. We're also going to have an add assign, which is going to actually modify this. Now you'll notice that in the standard, I think I mentioned this before, in the standard, if you do a pointer on one function, you wind up doing a pointer on all functions. I like to not have, this is almost like const to me, like in C++ when you say like this is a const function, this doesn't actually modify this guy. Obviously that's an object-oriented programming way of thinking, but it's nice to explicitly do that because I'll get actual compile warnings if I try to do things incorrectly here. So that's just a preference of mine. You should probably follow the standard, but we're not going to here. And we're going to have subtract assign. Awesome. Oh, I don't know what it's doing here. No, you don't. What? Oh, sorry, I didn't even see it doing this. No, you don't return anything here. This is the problem with generated stuff. You got to pay attention. Okay, so now we're going to do our multiply, which is going to just multiply these 2 together. And then we're going to have a multiply assign. It should figure this out by now. And we have divide. Yep, I want that. And then we have divide assign. It's kind of all straightforward stuff. Now we're going to have a scale, vvec3 scale. And we're going to pass in a scalar and return a vec3. And I have one called a shrink. I don't know if that's what people normally call it, but um, I like it. Shrink is divide. Yeah, I knew what I was talking about. So next we're going to get the length, 3, and we're going to start being a little bit more rigorous at checking what this is producing, just so that we know that it's not trying to do any kind of weird stuff here. So like this is the square root of the v length squared. Like this function doesn't exist. It's just assuming off some open source stuff. We're just going to do vec3 dot vv here. We haven't created the dot, but we're going to. So now we're going to do length squared, which is not going to be that. Oh, well, xx plus yy plus zz. Yeah, I guess that is. Why even have a length squared? I don't need the length squared. So let's do the normal. Just doing these in the. I don't want to normalize. I want the normal. And the normal shrink 1 divided by the length. Shrink scalar. The length. No. Let's just because I have it done a different way, we're going to do it the way that I have it for now. We can check out that suggested method later. I don't have time to super check all the math that it's producing because it's better just to go with what I've used before, which works completely fine. Normalize. Okay. And now we're going to have a negate or a negative. Negative. Thank you. And we're going to have an inverse. And this is just going to inverse itself. Then we're going to do the cross product. We're going to do this as a package function. Vec3 cross v vec3 other vec3. And let's see. Should be the y multiplied by the z minus the z multiplied by the y. Then it's zx and xz, and then it's xy, and then yx. Okay. If you're coding with AI, never trust the AI, especially for the mathematical stuff. It can be right most of the time, but don't just think that it's right, especially when you're developing software that's not just, for fun. Be diligent and learn. So we're going to v.x ty. I don't really use this function all that much, but I like to have it. And you'll notice that I will do different forms of initialization of variables, where I may use the var form and I may use the equals form. I have no preference to either. They're the same thing. Okay, let me make sure this is right. So tx less than tz, then the other is going to be, we're actually going to put in vec3 right here. Some static functions we're going to make. Vec3 forward, vec3 up. Makes it a little more readable. Vec3 forward. And this is if the ty is less than tz, okay? And then we're also going to return vec3 cross v and other. That's correct, actually. Okay. So next I have an approximate function, which just checks if two vectors are approximately equal. And we're not going to use this epsilon, we have some built-in Go stuff we can use here. Also, where's the cross? Let's make this, there we go, just so it's consistent. Let's code. Okay, so the vector3 approximate is going to return the absolute value of a.x minus b.x is less than epsilon is going to be math dot smallest near zero float 32. We could probably make this into a different constant based on whether we're doing float 64 or float 32. So this may be a come back and double check later scenario. So all these should be pretty straightforward. Okay, so this math didn't want to come in. Oh, there it is. Okay, just took a minute. And these, let's make these A and B. So this absolute value, if we look at the math library, the absolute value takes a float 64, and we could be dealing with a float 32. So as part of our configuration, we're going to create a couple of helper functions for our math library. Okay, so you could deal with generics and all that sort of stuff to set this up, but actually the way that I prefer to do it is to make a float32.go and a float64.go, just so that we can select what we build with. So the way that we're going to do with this is we're going to say go build not f64. So if we do f64 as a tag, oh sorry, am I in the 64? Okay, if we do float64 as a tag, I'm going to take this type and move it over here. It's going to be float64, and if we do float32 as a tag, it's going to be, or if we don't do float64 as a tag, it's going to be float32. So by default, it's float32. Now these are going to have a bunch of functions that are identical between them. We're going to have an absolute value function that we just saw, and we're not going to do that. We're going to actually use the built-in return math.abs. This should get inlined for us. And then we're going to do a few other things. Min, max. We're essentially going to go down the gambit of these math functions. Min, I think I can pause the video on this one. These are all going to be pretty much identical to the math function calls. Okay, so I did absolute value, min, max, a cosine, square root, log 2, floor, ceiling, sine, the sine, cosine, tangent, arcsine, arctangent, arctangent 2, and pow. And all these are built-in functions, so pretty straightforward. We're just wrapping all of those functions. And now we need to make the float32 equivalent to all of these functions. So I'm just going to copy this block and paste it down here. And of course, they're going to complain because float32 doesn't have these. So I previously went through and kind of went into the float64 package, figured out some of the stuff I can take, and then worked with that. So we're going to return math.float32 from bits, and we're going to pass in math.float32 bits. Oops, bits x, and we're going to, is that correct? And or 1 shift 31. Okay, so this is going to be our absolute value. Our next one, our min, is going to just be float, and we're going to cast these. So a lot of these are just going to be casting as a float 32. So let me check how many of these are just casting. I think most of them are. Yeah, so all the rest of these are going to be casting. So I'm just going to select here, 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 all the ones with single arguments. Asine, Atan. Okay. And then we're just going to take this and we're going to say float 64. And then we're going to cast the whole thing as whatever float is. And now for the ones with two arguments, do float, and then we're going to do float 64, float 64. There we go. So now it just casts them as float 64 and calls those functions. We can optimize those later. So that gets us going to where we are making this vector3 approximation happy. So let's continue on with our other functions. Func vec3 min, a, b, vec3, and let's see if this is correct. We want to return the minimum of ax and bx, ay, by. Okay, so that's right. So now we're going to do a max, which is going to be a mirror of that. And let me make sure x, y, x. Okay. Func, and we're going to do a vec3 min abs, which is going to give us the absolute value of our, or it's going to give us the minimum absolute value, and then the max is going to be the same. Now we need an absolute value. The vec3 absolute value, vec3 return vec3 abs. Yeah, okay. And now we're going to get a distance. The vec3 distance other. And what we're going to do here is we're going to do v.subtract other.length. Okay, now we're going to do a dot, func vec3 dot v other vec3. This is just the dot product, just double checking it, x times x plus y times y plus c times z. Okay, we're going to have a vec3 lerp, and this is going to take in a from to vec3 and a t float. So here, what is it doing? No. Return from dot add to dot subtract from dot scale t. Okay. So now we're going to do our string functions. Func vec3 from string, and this is an arbitrary stringification that we're going to be doing. It's basically just comma separated. So let's see. Let's do comma separated, just because it's more readable to me. Okay. So now we're going to have a string function. The vec3 string, and we're going to return the exact same format. I could probably make this format into a const. Vec3 str format is equal to this. So we can change it and reference it later. Let me just stick this up here. Okay. So now we're going to have a func v vec3 angle other vec3 float. Return the arc cosine of the vec3 dot from v and other divided by v dot length times other dot length. Okay, and then we're going to have a equals vec3 equals other vec3 bool. Okay, and that's just going to do the approximation function for us. So now we're going to drop in all of those helper functions that we were previously setting up. So we're going to have vec3 up, we're going to have vec3 down, vec3. Actually, the AI should be able to help if I just do the first one. Func vec3 up, vec3 return 3. All right, let's just say vec3. There we go, up. And then I want func vec3 down, -1. Okay, and then I want left, which is going to be -1 there, and right. And then I want forwards, which is going to be -1, not +1. And backwards, which is going to be +1. And that's just because we're going to be dealing with Vulkan, where forward is the negative axis. So now we want a 0, a 1. I want a func vec3 half. And then I want a func vec3 largest, which is going to return the max float 32 on all three of the axes. Let's do the func v vec3 square distance. I think I said we don't need this, but whatever. I have it on here. Might as well throw it in. Return. We're going to do, it's basically vx. Oh, I think this is it. Let me see. This is a lowercase y. Okay, vx bx times vx bx negative bx, yeah, or minus plus vy by vz vz. Okay, and then func v, what is going on? V vec3 largest axis. And then we're going to return the largest axis of the three axes. No, I don't need absolute value. I don't know why it thinks I need absolute value. Okay. The max, what? Oh yeah. Also, we have, and the newer version of Go, we have max built in, so I think I can just do this guy these days. Which can replace some of the other max stuff we have, but we'll deal with that when the time comes. Now, lastly, we're going to have a multiply with a vector 3 here, or a matrix 3 by 3 here. So let's stub in the matrix 3 by 3. I'm just going to call it mat3. Typically, I just, if it's the same dimension, I just name it with the single number. So this one is similar to the other one. We're going to do type mat3 is a 9 float. And that should be good enough for us to do what we need to do. Okay, I was just looking at my notes here, and I want to go to this config, and rather than this, the vx, vy, and vz being set to an explicit int, I can do a type vector component equals int. I think I use an equals there. Vector component. There we go. And that's because I don't want to use vx, vy, vz, vw for quaternions. So I'm going to make a separate one, Quaternion component, duplicate this guy, but obviously different order. And these are going to be Q. Bring the W up, bring this here, oops, and make this a Quaternion. Cool. Anyways, so now that we have that, we can finish off our vector 3 here with our multiply matrix function. So v vec3 multiply mat3. RHS is going to be the matrix, mat3, vec3. Now we're going to, var result is vec3, and we're going to return result. And now our contents is just going to be row, RHS dot row vector. And this is a function we've got to make. Result vx is equal to the vector3 dot, and I like to do it in this order. Doesn't really matter. Then we're going to reassign the row to 1 and 2. And then just change our components here. Vy, vz. We double check that. Okay, cool. So now we're going to want to have our row vector function for our matrix 3, which we can just throw in here. I have func m mat3 row vector row int vec3, and we're going to return vec3 m row. We don't really need the +0, but I guess we'll leave it there for quote clarity. And let's also throw in the column vector in here as well. Let me make sure that's right. Column +0, column +3, column +6. Okay, cool. Yeah, so that's our vec3 stuff done. Now we have quite a bit more to go. We have vec2, vec4, matrix 3, and matrix 4. But they should go a little bit faster now that we have the vector 3 in. So let's just finish up this matrix 3. I don't have a whole lot for it because I don't use them too much. Let's make a function for creating a new one. At 3 identity. Func at 3 identity mat3 return. Let's see if it figures it out. 1, 1, 1. Okay, easy enough. Okay, and then we're going to get a 0 just for readability. Mat3 0. It's pretty straightforward. We're going to get a mat3 from a mat4. So we should stub in a 4-dimensional matrix here. mat4.go package matrix. Change this to 16 and change this to mat4. Okay, so we have it there. Okay, so func mat3 from mat4 m mat4 mat3 return. See if it figures it out. 0, 1, 2, 4, 5, 6, 8, 9, 10. Okay. Func m mat3 to mat4. Mat4. Return a mat4. Yep. Okay, and then the last one. Cool. So now we're going to have a reset function. I like this one to be like reset to identity. Mat3 reset. And then here we can set it equal to identity. I don't know if this is faster or if it's faster just to, I don't think it matters too much, but I'll do it this way. Okay, I just paused the video to add those in. We're going to have the row and column there, and then we'll have the multiply, so you can multiply 2 of them together. Now, this code was transferred from my C project, so it may look a little strange. And also, I had a lot of vectorization, and for Android, I was using the Neon vectorization library, which is not exactly the full range, but doesn't have 256 bit operations, but it was able to. Anyways, I was able to make it work out with larger vectors. Okay, actually, I'm gonna leave it as this. This looks fine. I was doing some fancy pointer stuff in C, and I copied that over verbatim rather than just doing it this way and Go. I'll have to work out vectorization a little bit later. So the last one here is going to be func. Actually, we need a multiply vec3 in here. Oh, let me double check these real quick. 0, 1, 2. Okay. 0, 1, 2, 1, 2. Okay. 0, 1, 2, 0, 1, 2. Okay, cool. And then we're going to have a scale. M at 3, scale, vec3. Oh, I guess this is. Wait, these are the same thing. Let me. Yeah. Yeah. I don't know why I called it scale. Multiply vec3. Yeah, we don't need both those. That's silly. Got to take out the trash cans. Let me snooze that guy. Okay. So now we have our vec3. That's pretty much all we're going to do to it. So now we've got 2 knocked out. What I'm going to do is I'm just going to copy the vec3.go now. Go to vec2go, paste it, and then we're going to locate anywhere in this file where we see vec3 and replace it with vec2. And we are going to paste it on the capitalization. And then anywhere we see vec3, we put vec2. And we change this format down to 1 component, change this to 2, get rid of the z's, change this to xy, change this to, actually, do I have it as vec3 there? Yeah, I don't have the as vec2 at all. So get rid of all the vec-z stuff. Now, what I do have that's special here is I have a func v vec2. I have a couple of extra functions actually. So outside of x and y, I'm going to duplicate those. And I'm going to create extra helper functions. One's for width and height. That way we can use this vec2 effectively for dealing with widths and heights. Then we're going to have set width, set height. Those are the same thing. Technically, I can just wrap the other functions in them since it'll inline it, but we'll just do it this way. So now we got to go through and get rid of all the z's. And that'll be pretty much it here. Get rid of the z. Get rid of the, oh, this will be as aligned 16. We don't need this because it's 2 bytes and that aligns well with the GPU, so we can get rid of that guy. I like these ones because it's easy to just cut the line. Subtract. Scalar. We're basically going to be doing the same thing for vec4 except adding a component. Now, I don't know if we really use the length all that much. Let me see what I did in mine. Yeah, we have length. Of course, we have normal, negative, inverse. We don't need a cross. Let's get rid of the cross product. We don't need an orthogonal. Get rid of that. Approximate, min, min absolute, max, max absolute, absolute, dot. We don't really need the dot, but I think we'll keep it just because it's used in other functions. Vec2 lerp. Let's get rid of these guys. Up, down, left, right, forward, backward, 0, 1, half, and largest. Square distance. I doubt I'm going to use this. I'm actually just going to delete that guy. Largest axis. And we don't need this. Okay, so now we're done with the vec2. We can now move on to the vec4. And again, we'll just copy vec3, paste it. Oops, I copied matrix 3, vec3. Paste it. We're going to do the same search and replaces here. Search for vec3, replace it with vec4. Search with an uppercase vec3 and replace it with uppercase vec4. Change this to a 4. Add in that. Add in a W component. W. Oops. Set W. And then we're going to have an asvec3 function. VZ. I don't know if we need a vec2 function. That seems kind of odd. So there's two halves. XYZW float VVW. Now we're also going to have the vector 4 is similar to vector 2 where I use that for width and height. And the float 4 can be used for, say, left, top, right, bottom, and also a box. So you have X and Y, width and height sort of thing. So we're going to have helper functions for those. Okay, and also as vec3, we can actually just return everything up to the third component, or I guess technically everything up to VZ. And that should be, so I kind of complain because it's not exactly, let's keep vec3 in there, and VZ, row. We're not creating a new one, we're casting it. Okay. Oh, while we're here, might as well do that to this other one too. Vec2 cast V up through Vy. Okay. Cool. So here we're going to add in these guys again, except this one's going to be left, top, right, bottom, and then I'm going to have, we don't need pointers to left, right, top, bottom. We can have setters. Set left, top, right, bottom. And then we're going to take this, the left and top are fine. We're going to take the bottom, the right and the bottom, and we're going to also add in a width and a height as helpers. Set width and set height. Okay, lots of helpers there. Now back to standard programming. No pun intended. So here we're going to do float A3. Oops. Float A0, float A1, float A2, float A3. This needs to be A4. Did I fix that in vector 2? Nope, 2. Okay. Now we have copy paste that. 3. Okay, we don't need aligned 16. It is aligned 16. Let's see if the AI can help us here because I'm being a little lazy. So add that in there. Add that in there. That there. There. I'm just checking these as I go to make sure it's doing it properly. It can't figure out what it's going to do here. There it goes. Now I'm going to do it here. Here. Got to be careful here because the compiler is not going to tell me if I'm not setting the fourth component. So I'm going to pay pretty close attention. Oh, this is a cross. We don't need a cross for vec4 or orthogonal. Proximate. And distance. Oops. W. Lay. I don't need angle. I guess I can leave it for now. Let's see. I don't need these guys. 0, 1/2, and largest. Square distance. I don't really use largest axis. Multiply vec3 is going to turn into multiply vec4 for mat4. And we're going to do the same thing, but oops. This to 3. And this to VW. Oops, W. Okay, and we'll create those row vector and column vector pretty much the same as this one's row and column here. 4, but we're gonna have to change up the math here. So let's just see if it gets it. No, that's for vec3. Thank you. 0, 4, 8, 12, 4 plus 0, 10, 4. Okay. So now that should make that guy happy. And we're just gonna have a couple of extra helper functions for screen stuff. So vvec4 box contains xy float bool return v.x is less than or equal to x and v.x plus v.z. Oh, I guess width is good there. Width is greater than x. Let's see if it figured this out. X is less than x, or x plus the width is greater than x. And the y. Okay, I think that looks about right. So now we're going to do a func vvec for area contains, and areas are going to be kind of like top, left, right, and bottom. So this one's a little easier. So we're just going to do x is less than or equal to x, and v dot z is greater than or equal to x. Actually, instead of v dot z, we can do v dot right is greater than. Okay, that figured out the rest. So now we just need to add in a screen area contains. I think that's the same thing. I don't know why I have that twice. Okay. Oh, screen area contains is the same thing except it's in screen space, so the y's are swapped. So area contains, this one should be greater than or equal, less than equals, and this one should be the way that we had it. Cool. And this is screen area contains. Okay. So that's it for our vector 4. It's completely set up. So now for our last beast, which is going to be matrix 4, and that one's going to be quite a bit of stuff. Okay, well, let's get started. No need to keep putting this off. So we're going to create a couple of consts here. Const, we're going to do mat for row 0 is equal to iota. Then we're going to do row 1, row 2, row 3, const mat for column 1, 2, and 3. And then we're going to have a bunch of helper xy's just for readability. So we're going to have x0, y0 is equal to iota, x1, y1. Just making sure these are going in the right order. 0, 1, 2, 3, 0, 2, 3. Okay, so we have all of those as helpers, and then we're going to create a couple more helpers. So these are all private because they're lowercase, just so that there's less typing going on here. But we're going to make some public ones that, I guess we can make them public here because this is a matrix library, so it would make sense to be, matrix.x0y0 whenever we use it. So I didn't name my package matrix previously. It was either algebra or mathematics. So yeah, I think we're good. So like the mat3, we're actually just gonna copy these ones. Reset and new. We'll get rid of the ones we don't need. So mat4 is going to be a mat4 identity. This is going to be a mat4 identity. 0, 0, 0, 1, 0. Did I forget a comma? What are you complaining about? Oh, mat4. 4. Okay. Mat4, 0. Let's see. I'm not going to... I already have from mat4, so I don't really need that guy. And then we'll get our reset here. 0, 0, 0. So 4 is going to be 0. This one's going to be 1. Going to be 0. 9, 10, 11, 12. Guess I should use my... the problem with... the problem with doing this is that you might think x1, y1 is for the matrix 3 when it's actually for matrix 4. So I'm going to put these back to being lowercase. Maybe that was my reasoning. And then we're going to have another one for the public mat4 equals that. Okay. So now those are exposed to and known. And these are just going to be private. So let's actually use our values here to do this reset. Okay. So when we're dealing between OpenGL and Vulkan, the x1, y1 is inversed. So I have a special function here just so that we know what to do with Vulkan. I call it map4 projection to Vulkan. And this just takes in we're just taking the current one and we're inversing the x1, y1. It's very straightforward. It doesn't modify the one that's already there, but it's making kind of a copy, and that it could be annoying. I don't know. Optimization through tracing and performance checking. Don't need to optimize now. So I'm actually going to copy in some blocks that I have from my previous stuff for this matrix just to make it simpler. We're going to bring in a project function here. And the multiply vec4 function is coming, but this is just a project function. Then we're going to bring in an unproject function. This one just projects into 3D space from the screen, and this one is going to take a position from 3D space and project it to the screen. That's the difference between those two. I'm just going to move this stuff up here because we're just going to start to get into the meat of it here. We're going to need to, I guess I'll add, so we have row vector, column vector. We're going to also add a map4 at row index, call index, int float. And we're just going to return row index times 4 plus call index. Okay, just because I'm not going to type it, here's the transpose to transpose the matrix. We're going to add in a transpose assign, same thing, but it assigns the current one. We're going to add in we have a 0 function. No, we don't. I'm going to add in a 0 function here. It's less than 16. It's very straightforward. I could just do the length of the array because it's an array, length of m. Okay, so let's see, we have our reset was already done, and now we're going to get into things like add assign. This is just going to add to this matrix, subtract assign, subtract from this matrix another matrix. We're going to negate assign, so we can just do a negative of all of these, and that should also just be the same kind of for loop here. We don't need a big old block of the same exact code. Times equals -1. Okay. Now we're gonna do the mat4 multiply. RHS mat4, and I have the crazy C code in mind, so I'm hoping that we can just, do the same. What is going on? It's just duplicating it. Okay. I think it's having a heart attack. Is that correct? Hold on, let me check this. Okay, that actually looks correct. So we'll leave that. We're going to have the multiply assign. It's going to be the same thing. See if it can figure it out nice and easy. What is this? I want it to look like this multiply sign. Bro. So let's just copy the first one and see if it does what I want it to. Okay, that's looking better. I don't care about duplicated code. We don't really math. The way you should think about this is math doesn't change. So we're not gonna come in here and be like, oh, we're gonna change. The math has changed here in 2024 or whatever. Okay, so multiply sign. So now we're going to grab our orthographic function. we're going to grab this function. Where is that function in my? Oh, this just needs to be. Wait a second. Right. So I have special. This is the where we use the Vulkan code. So we actually need to split some of our math here. We'll call it mat4.gl.go. This is for the OpenGL code. We're going to go build. This is for JS. If we use OpenGL as an arg or WebAssembly, and we're just going to say func mat4 x1y1 current float return current. Okay, and then we're going to have one for Vulkan mat4.vk.go. And we're just going to copy this whole thing, paste, and if it's essentially if it's not JS and it's not OpenGL and it's not WebAssembly, then we're going to do negative current. And this is the multiply that we saw previously. We did when we have the to Vulkan function up here. Oops, there we go. This projection to Vulkan. So that's the x1, y1, -1 that we see there. So that's that helper function. We can split that out by renderer. That's basically what that was. So now that we have the orthographic, we're going to have perspective. And these are just traditional functions for orthographic perspective. I worked them out with a lot of research and stuff a long time ago, so I've just been kind of copying them forward and for a long time. So I'm just going to copy and paste them. So now we're going to have a position, which gives us the position of the vector, the position component of the vector. We're going to have a translate, so we can move this vector by some position. I'm going to have a set translation, which just sets the position of this. It just assigns the position of this matrix. We're going to have a scale function, which is going to scale up the size. So if we had like a cube, we can scale it larger. So that's the scale function. We're going to have the look at, which just allows us to look at a given point, given an up axis. We're going to have a rotate, and then we're going to have special rotate functions for the x, y, and z. These, it's a long story. I think we'll get to it when we get into the transformations stuff later, but just know we have the rotation for x, y, and z, and this way we can rotate them independently. We can rotate along the x, then the y, then the z, or the z, then the y, then the x, etc. You can rotate kind of arbitrarily. So this next one is a big boy. It's called rotate angles, which takes in an axis that you want to rotate and how many angles, and it's a big old boy. You can look at it, check it out if you want to. We're going to have the inverse function. So obviously this is just a traditional inverse matrix function, nice and simple, so to speak. We're going to have our function for multiplying by a vector 4. Column vector, I thought we had this. Row vector. Oh, I spelled out column vector. That's fine. We can use the spelled out version. I like clarity. Now we're going to have transform point. This will make it so that you can pass a point into this matrix and it will transform the point in space given this matrix. So let's say that you had a cube that was rotated and scaled and moved off somewhere. You can take a point and you can transform it by the matrix that cube has. So now we're going to have functions for the right up and forward coming out. We're going to have a function to turn this matrix into a quaternion. That's what quat is. I might actually spell out quaternion in this version. Quaternion, quaternion. So let's find all quats and replace them with quaternions. And then we're going to have an invert function to invert this matrix. So obviously we're going to have errors where we are using quaternions. The degree to rad, that is a function that I have created in my in mind that we need to copy over. So inside of the config, we're going to add in a few things, a few helper things, a few more helpers. So we're going to create a type number interface, and this is going to be a constraints. Constraints integer and a constraints float. So any number there. We're going to have a type vector interface, which is going to be a vec2, vec3, vec4, or a quaternion, or or no, just those three. Yeah, let's throw in the quaternion. And that's a little different. We're not going to use this much. We'll see. So type matrix or interface. And we're going to have met 3 and 4. Now we're going to have our radian to degrees. I'm going to have function rad to degrees t constraints float. And this is going to be math.pi and rad. I like to spell out radian. So radian times 180 divided by pi. And now we're going to do a degrees to radians. Okay, what's this complaining about? Cannot convert 180 divided by pi untyped constraint 57.2958. Okay. We'll come back to whatever it's complaining about. Let's see if we need any more of these. I don't think we may not need any more of these right now. We still got to create the quaternion. So that fixes all those guys. And quaternion from Euler. And the rest are quaternions. So now we can create our quaternion. Quaternion.go. Type quaternion for float. Okay, so we'll bring in some of the functions that I have for my quaternions, but we have to change quat to quaternion because I'm going to spell it out from now on, apparently. And we're going to have similar functions to the vec4 and the vectors. Let's bring in our constraints. So from array, from slice, this allows you to create it from either float32 or float64, either one. But we're just casting it down or to whatever type we're currently using. We'll probably need to do a similar thing on our vectors. Vector2, t float. Yeah, we can do t constraint float, same thing. I think that's what I meant to do. Vec3, constraint float on those two. Vec4, constraint float on those two. Cool. So let's finish up our quaternions here. We're going to have an identity for the quaternion. And I should spell these out. Quaternion. Quaternion, new Quaternion. Return identity. We can create it from a vector 4. And we can check to see if two quaternions are approximately the same. And these numbers can also be changed. Also, look, it didn't even do the z. Oh my goodness, let's just copy the approximate function here from vec4. Instead of c, I would just kind of convert quaternions, and between quaternions and vec4, you just cast them as each other to do some stuff, which I suppose we could do here, but I like having them separate. So quaternion to matrix 4 is a helpful function. It does exactly what it says it does. Converts the quaternion to a matrix 4 by 4. Or wait, no, this is from matrix 4. Converts a matrix 4 into a quaternion. This is the 2 matrix 4. So that's the one we'll do there. We want to be able to create a quaternion from Euler angles. Euler angles, I'm sorry. From Euler. And we need a 2 Euler. Oh, we did need my clamp function from the other one, or from the configuration. Okay. It just was choking for a second, so my voice, I might have to give it a minute before I continue. All right, I think I'm pretty much good. So we're going to do max. Actually, let's change these to current minimum. Oh, wait. That's minimum maximum. And then we can, instead of doing this casting, we would just do max. Oh, wait. Max min. There we go. So now we have our clamp here, which was missing from that one. A few more functions coming in. We have the, these are local functions for scale, quaternion dot, I like quat dot, but we're going to change it to quaternion dot to keep it uniform. So now we have scale assign, normal, normalize, the usual suspects that you expect. We're going to throw in a lerp, and we're going to throw in a slurp. So lerp is linear interpolation. Slurp is a spherical linear interpolation. I accidentally stopped the recording when I was deleting those, so forgot what I was saying. Oh yeah, spherical linear interpolation. So this would be from to quaternion, from to quaternion, quaternion there, quaternion there. And now we'll continue on with the next few functions just to see what all we have. In here, we're going to axis angle function, an inverse function, a conjugate function, pretty straightforward quaternion stuff. Multiply assign function, similar to all the other multiply assigns we have. And then we have a multiply vec3 function, which is self-explanatory. You can multiply against a vector 3. Add assign. a quaternion angle between, which gives you a quaternion, which is the angle between two vectors. Quaternion lookat is our last one here. So this just makes is a helper for getting. It's kind of like how you use the matrix lookat, where you can make a rotation matrix to look at a given point, given an up axis, an eye level, and a point similar to that. So from this point to this point, create a quaternion that creates that lookat there. So with that, I think we've satisfied pretty much all of our major feats that we needed to satisfy. There's a few other things we need to make, such as vec3i and all of those sorts of things, but we can make those as we need them a little bit later. Those are mostly helper stuff. The constraints for float, I don't think we need to go through the hubbubaloo of including it in this guide just for constraints float. When we're using it here, we can just create that float constraint. I'll create it down here with these other ones. Type float interface float 32, float 64. Oh wait, I'll call it floating point. Yeah, floating point. Constraints floating point. Because float we're using for pretty much everything else in that one type. So now the last thing we need to do, are we using these anywhere else? Oh, we are using them in quite a few of these. Let's just change these to floating point. Floating point. Okay. Now for our last guys, whatever this is complaining about, cannot convert 180 divided by mathpi. Okay, it's so. Let's change these to floating point. There we go. Now it's happy. Cool. Get rid of this. We don't need that. Why do you still need it? Constraints integer. Oh. I guess we'll just make our own constraints integer. What we are going to do is be a little bit lazy though. So we can just pull up the page for, oh, I forgot to use the squiggly on the floats. Integer, signed and unsigned. Oh, those are down here. This is an experimental package. I don't know when it's going to not be experimental. Maybe it's not. Let me see. If I go constraint, this one, build constraints. Okay. Yeah, let's just, I think it's easy enough to copy over these. They're such minuscule things. So integer. Let me just put this on the other monitor. Okay, so we have our integer, and then we're going to have our signed and our unsigned, and we're going to have our integer here. Floating point needs these to have the little squiggly for the derivatives or of them. Okay, cool. Awesome. I think we are done with our mathematics stuff. We're not using anything, so building likely isn't going to give us much of anything there. Cool, but it is still building. All right, so that's going to be all of our mathematical stuff. Um, and now we can begin on some more entertaining things. Cool. Thanks for watching.